Hello, futurist. In the rapidly evolving race towards quantum advantage, IBM is taking a bold leap forward with Starling, a fault-tolerant quantum computer projected to debut in 2029. Starling represents a transformational shift from today's noisy, error-prone quantum systems to a new era of reliable, scalable quantum computing capable of tackling real-world and irretraceable problems. Built on advanced error correcting architectures and breakthrough quantum chip engineering, Starling aims to unlock unprecedented computational power for science, industry, and society. This video explores the vision, innovation, and impact behind IBM's most ambitious quantum milestone, yet laying the foundation for a future where quantum computing becomes truly practical. Join me on this journey of the future now, where we explore the technologies that are transforming the present and shaping the future of tech. Watch this entire video and let's get started. Building Starling, IBM's fault tolerant quantum computer coming in 2029. Introduction. IBM's quantum computing announcement might not have been as flashy, but it was quite revealing. Not unlike looking through clear liquid glass, IBM's announcement lays out a remarkable concrete roadmap to deliver Starling, the first large scale fault tolerant quantum computer by 2029. Housed in a new IBM quantum data center in New York, Starling promises to execute some 20,000 times more quantum operations than any system in operation today. That's some marketing hyperbole, as representing its state would require memory equivalent to over a quadrillion or 1048 times of today's fastest classical supercomputers. This isn't IBM's first quantum roadmap, but it is the first time the company has publicly laid out detailed processor milestones. Loon in 2025, Kokobora in 2026, Cockatoo in 2027, accumulating in Starling at 2029. Each testing critical elements of error-corrected modular architectures based on quantum LDPC, low density parity check code, or QLDPC, quantum low density parity check codes, to slash qubit overhead by 90% relative to previous codes. In plain terms, IBM is tackling the quantum equivalent of the classical vacuum tube to transistor transition, which is nothing short of revolutionary, if you ask me. Let's keep watching.
Google just built a computer that solved a problem in 5 minutes that would take our best supercomputers 10 septillion years. It's not a typo. That's 10 with 24 zeros after it. The universe is only 13.8 billion years old, so we're talking about a computer that just did something cosmically impossible. And Google isn't alone. Microsoft and Amazon are racing to crack quantum computing too, each with wildly different approaches. And after decades of being the much hyped the future, quantum computing suddenly feels like it's arriving all at once. So what changed? And should you care about computers that need to be colder than outer space to just work?
Journey from ENIAC to quantum entanglement. To appreciate Starling's significance, we need to rewind to the dawn of programmable computing. Yes, you are right. It's time for a much needed history lesson. In 1946, ENIAC, Electronic Numerical Integrator and Computer, a 30-ton behemoth, calculated artillery tables at just 5,000 additions per second. A few years later, IBM's 650 drum memory system at roughly $500,000 per unit became the first mass market computer, steering in an era of batch processing for business and science. IBM's history is intricately intertwined with both classical and quantum threats. In the 1950s, IBM's transistor-based computers replaced vacuum tubes, notably with the IBM 1401 making data processing affordable for mid-sized businesses. A decade later, System 360 pioneered architecture-compatible families, defining the mainframe era. Fast forward to 2011, that's when IBM launched the first 5-qubit quantum processor at Yorktown Heights. Each subsequent leap, 16 qubits, 50 qubits tested, coherence times, and basic algorithms, but remained NISQ, noisy intermediate scale quantum devices, limited by error rates and decoherence. It wasn't until IBM's Nature cover paper on quantum LDPC codes that a clear, efficient path to error-corrected logical qubits emerged. Now with Starling and beyond, IBM is unteaching decades of hardware, control electronics and algorithm research into a practical vision. 100 million qubits operations on 200 logical qubits, followed by 1 billion ops on 2000 logical qubits with Blue Jay in 2033. This roadmap is more than ambition. It's a stepwise de-risking of large-scale quantum computing, much like IBM's systematic moves in classical eras. What's so special about fault tolerance? Classical hardware, which is what all our modern PC, laptop, smartphones compromise, is remarkably reliable. Bits stay intact and errors are rare. Quantum systems, by contrast, suffer from noise, where stray electromagnetic fields can flip qubits states in microseconds. Fault tolerance, then, is the foundational pillar of quantum computing's promise, where thousands of noisy physical qubits are bundled together into a single logical qubit whose error rates shrink exponentially with cluster size. IBM's papers detail how QLDPC codes and real-time decoding with classical processors will keep these logical qubits coherent or clear long enough to run meaningful algorithms. It's the quantum counterpart of error-correcting memory in classical RAM, but orders of magnitude is more complex. Achieving this at scale without insane overhead was a long-standing hurdle. Starling promises to break that barrier. The quantum computing road ahead. What's the need for quantum computing? Think of it this way, that classical computing gave us the internet, climate models, and AI that warns us of pandemics. But certain frontiers, like simulating complex molecules for drug discovery or solving massive optimization problems, remain provocatively out of reach. This is where quantum computer shines. IBM Quantum Starling stands as the next great expedition into the great unknown of computational limits. If delivered by 2029, it will let chemists model reactions at quantum fidelity, economists optimize vast portfolios, and cryptographers test new protocols. And just as the transistor's debut reshaped society, so might this first fault-tolerant quantum turn a significant scientific corner. IBM's role in all of this is unique. Pioneering transistor-era hardware, building mainframes that powered global commerce, and now forging quantum architectures. Few organizations possess the cross-disciplinary mastery to span vacuum tubes to qubits. Yet, one can't help but be pessimistic about their ambitious timeline, because classical progress took decades per leap, but IBM's quantum research team must compress that into a few short years lest other players, academia, startups, or global rivals capture the lead. Yes, IBM isn't the only tech company fiddling with quantum computing breakthroughs. There is Google, Intel, Amazon, Microsoft, and few others are also in the race. Refer to the Future Now playlist for more videos. For ENIAC vacuum tubes to the IBM System 360s, transistor logic, from Google's Willow chip demonstration to today's IBM's Starling blueprint, we are witnessing a continuum of human ingenuity. IBM's new roadmap doesn't just chart a technical path but aspires to create a computing revolution. As we count down to 2029, the real question isn't just whether IBM can build Starling, it's whether we can harness its power responsibly to tackle the world's most pressing challenges. I hope you enjoyed this video and gained valuable insights into the latest tech innovations. The future is now and the possibilities are endless. Stay tuned for more exciting deep dives at profound insights under the Future Now, the latest in tech playlist. If you like this video, please remember to click the like button, subscribe for more exciting tech updates and share your thoughts in the comments below. Your engagement motivates me to create more content like this. Until next time, stay curious and keep innovating. Thank you.